All right, let's do an actual example of a two-dimensional collision. I've subtitled this, Will This Collision Make a Sound? And you will see why that is the subtitle in just a few moments. The problem that we have here is a glancing collision. It's not a head-on collision. Our 2 kilogram object is initially moving at V2 initial equals 27 meters per second horizontally. And it collides with, in a glancing collision, this 1 kilogram object, and they both move off in both X and Y directions after the collision. And what we are given here is that V2 final is 22 meters per second at 23.2 degrees below the horizontal. And our question that we're trying to solve is, what is V1 final? So that's one of the questions. The other question we want to figure out is, within uncertainty, does this collision make a sound? Now, what does that have to do with momentum or collisions or anything like that? Well, we will soon find out. So let's take a look at first, what is V1 final, the final velocity of the 1 kilogram object, which I'll just label here as object 1. In order to do this, we've got to appeal to the law of conservation of momentum. And that is the initial momentum of the system will equal the final momentum of the system. Notice that these are both vectors. So that means to analyze this, we are going to have to split this into X and Y components. Notice I've set up my little table here. Great way to deal with X and Y components. And I've defined the X direction positive being to the right and the Y direction positive being up. Let's analyze the X direction first. In the X direction, we'll have conservation of momentum in the X direction, which means that the initial momentum of the system in the X direction will equal the final momentum of the system in the X direction. Now for the initial momentum of the system in the X direction, I've just written P2 initial X. What happened to P1 initial X? Well, because object 1 was at rest, I just left that out. It is 0. Its momentum in both directions is 0. And notice that I do have to include both objects in the final momentum calculation, both P1 final X and P2 final X, the momentum of object 1 in the X direction and the momentum of object 2 in the X direction, respectively. So what I want to do is figure out the final momentum of object 1. That's what I'm trying to find. So I'm going to subtract from both sides P2 final X, the final momentum of object 2. And that leaves me with P1 final X, the momentum of object 1 in the X direction, all by itself. Now I'm just going to get a little bit more specific here and plug in the expression for momentum. P2 initial in the X direction is just M2 V2 initial in the X direction. The mass of object 2, which is 2 kilograms, times its velocity in the X direction initially. And the subtract from that P2 final X, which is just M2 V2 final X. That will all equal M1 V1 final X. So I've got to solve for V1 final in the X direction. I just divide both sides by M1, do some plugging and chugging, and there we go. I've got 2 times 27, which is M2 times V2 initial in the X direction. There's only initially an X velocity. But then I got to subtract M2 V2 final X, and notice that what I'm doing there is I'm taking the X component of the final velocity of object 2. So that's just use the cosine and then divide by M1, which is 1 kilogram, makes it easy. We can see that V1 final X, the velocity in the X direction of object 1, finally after the collision, is 13.6 meters per second. Halfway done. Let's go to the Y side. Again, I've got P initial in the Y direction of the system will equal P final in the Y direction of the system. But notice that I've again left out P1 initial Y. Why did I leave out the momentum of object 1 initially? It was at rest. That was just 0. So let's go on to the next step. I'm again trying to find the final velocity of object 1. So I'm going to isolate the momentum of object 1. But notice that I've got P2 initial Y is also 0 here. Why is that? It's because it's moving horizontally. It's got 0 momentum in the Y direction. So now I can isolate P1 final Y on the right. Notice I get negative P2 final y. And then I just get a little bit more specific here. P2 final y is just M2 V2 final y, and P1 final y, M1 V1 final y. Notice they're going to be opposites of each other. And we could see that they both initially had zero momentum in the y direction. So finally they have to have zero momentum in the y direction. Thus, they must have opposite momenta. So let's go ahead and solve for V1 final y. We get negative M2 V2 final y over M1. Do some plugging and chugging here. And you will notice that in this step, I had negative 2 kilograms. But for V2 final y, notice I imposed a negative sign there because in my drawing, I'm just using reference angles of 23.2 degrees instead of the an angle like negative 23.2. I'm just using the reference angle. So that component of V2 final is going to be down. That's why I added that negative sign. It is going to be down. I've defined up in this picture as positive. So that down component of V2 final will be negative. And but notice that cancels out, so I get with the other negative, so I do get my final velocity of object 1 in the y direction is positive 17.3 meters per second. And you can see that what I have here is all I've done is created a vector diagram. Notice that my components, I'm using dotted lines. It's a really good practice. And I also have arrows on the components. Please do not leave out the arrows on the components. Very important. And then you can see I've got them drawn properly, so they add to my final velocity. And all I did here was just figure out the magnitude of it. It's 22 meters per second. It happens to be the same velocity as object 2, the 2 kilogram object has. That doesn't always happen. That's just a unique aspect of this problem. Just happens to have the same velocity. And notice that by using trig here, and using my inverse tangent of my angle, I can find out that that angle is 52 degrees above the horizontal. You could just express this in engineering notation and say, yes, the final velocity can be expressed as 13.6 meters per second I hat plus 17.3 meters per second J hat. That in itself describes V1 final. But now we've solved that problem. We got the final velocity here. The next question, though, is within uncertainty, does this collision make a sound? What's that all about? Really, what that's asking is mechanical energy conserved, or does energy leave this two-object system by thermal energy and or sound? This is just a fancy way of saying, does K initial equal K final? Is this collision elastic? In an elastic collision, and by the way, you don't have to say perfectly elastic. If you say elastic, that is perfectly elastic. In an elastic collision, no energy can leave our system. In other words, there can be no thermal energy generated. There can be no sound. Now, in actuality, any elastic collision, really you can't have two macroscopic masses because they will make a sound. But this really does work when charged particles collide because they actually never really touch. They will just bounce off each other due to their respective fields, and they really can collide with no sound. But for the purposes of this, we'll still see if this works. Does K initial equal K final? And we got to do this within uncertainty. My initial values were 2 sig figs. So all we can know for sure is if K initial equals K final within 2 sig figs, then looks like our collision is in fact elastic. So let's go ahead and figure this out. So K initial is of the system is equal to the initial kinetic energy of object 1 plus the initial kinetic energy of object 2. Now, I'm not going to split this into X and Y. Why is that? Energy is a scalar. We don't have to split it. K initial is just the sum of the two initial kinetic energies, K1 initial and K2 initial. And we can substitute 0 in for K1 initial. It was at rest when 2 slammed into it. So that goes to 0. So all we got to do is find the initial kinetic energy of object 2. It was a 2 kilogram object moving at 27 meters per second. 1/2 mv squared gives us 730 joules. That's to 2 sig figs. That's all I was given. So truly all I can use is 2 sig figs. Now let's look at the final kinetic energy. Again, direction does not matter. So I've got K final is K1 final plus K2 final. In this case, both of them have kinetic energy, but luckily I don't have to deal with X and Y. I just use the speeds, 1/2 mv squared. Their respective masses are multiplied there. And notice that I get 730 joules. I'm getting the same energy. So given that, kinetic energy is conserved within uncertainty. I only had 2 sig figs to start with. That's all I can really make any conclusions about. The collision is elastic. There is no energy released. Therefore, we cannot say that there's any sound made. No energy is released as thermal energy or sound as far as we can tell from our calculations. Now, I will say that these elastic collisions are truly very rare in macroscopic collisions. Elastic collisions happen all the time between atoms and molecules, but in macroscopic situations, it's really quite rare. So the one mistake you do not want to make is assuming kinetic energy is conserved. It almost never is. They would actually have to say kinetic energy is going to be conserved in this collision, or there is no heat or thermal energy or sound released. They'd have to pretty much tell you that's elastic. Very, very rare in our lab setting in macroscopic collisions. What you can count on, however, is that as long as there are no outside forces, the momentum of the system will be conserved. The initial momentum of the system will be equal to the final momentum of the system. Whether objects stick together, bounce apart, or even if they all slow down or even come to rest, momentum is still conserved. And that system momentum is equal to the sum of all the individual momenta of the objects in the system. For example, m1 times v1 plus m2 times v2 plus m3 times vector v3. You add all those up all the way to number n, the last one in the system, and you've got the system momentum. So I'll just throw one more equation in there, which can also be expressed like this. The mass of the system, the total mass, times the velocity of the center of mass of the system.